This session is The Beast Wins Again, Why TLS Keeps Failing to Protect You. The speaker is Antoine Delina Lavu. He wants you to visit the following link for the video in his presentation in case you can't see the one that he's going to show you. That link is bh.ht.vc. Without further ado.
Thank you, David, for the introduction. Hello, everyone. Please bear with my French accent. I'm really sorry. I'm a PhD student at INRIA in Paris, and the topic of my research is proving security properties about real-world websites. And for the past year, I've actually been working on TLS because it turns out that every security property of website I wanted to prove was relying on some strong assumptions about the security of TLS. And the more I try to verify these assumptions about the security of TLS, the more attacks I discovered. Unfortunately, I was assisted by very expert colleagues, both at INRIA and Microsoft Research, and they deserve some of the credit for what I'm going to show you today. So, despite the title, which is a little bit controversial, this is not a media bait kind of talk. It's actually a little bit academic, so please don't fall asleep. I'm going to wake you up with 3 attacks. So this is basically the outline of the talk. The very important thing to remember from this talk will be the common points, the common patterns you will find between these attacks. And I really want to show that the attacks that I'm going to demonstrate, they are in fact using very well-known vectors. And the fact that we are able to mount new exploits using these well-known attack vectors is a clear sign that we still haven't solved the problems we have with HTTPS. All right, so first, why do we want TLS? So I think many people in this room probably believe that the main reason why we care about TLS is for confidentiality of passwords and cookies. But in fact, it's really not the case. It's very easy to build websites that are protecting passwords and credentials against a passive attacker, someone like the NSA who is just watching the packets but not touching them. Actually, the main reason why we use TLS is because of its authentication and integrity goals. And these are the ones that are useful when you're facing an active network attacker, which is to say, a man in the middle. As for privacy, there's a widespread belief that TLS is helping with your privacy. And this is, for the most part, completely false. You don't have to assume that TLS gives you any privacy, because someone who is watching the packets on the network can very easily tell which server you are talking to, which page you are looking at. If you're maybe doing some search requests on that website, the attacker can probably also get what is the search term that you entered. And all of that because of side channels. Okay, so another thing is what is the expectation of webmasters about TLS? So webmasters are very familiar with the web attacker model. They know that very well, so we assume that the attacker is controlling some malicious websites, and the user is visiting both honest and malicious websites at the same time. And already this is a very powerful, very expressive attacker model, and there are so many well-known attacks, CSRF, XSS, redirection attacks. On the other hand, the network attacker is someone who is controlling the packets on the network. And of course, you have to assume that the network attacker is strictly stronger than the web attacker because the network attacker can inject himself into any HTTP website the user is visiting. And what people commonly believe is that if you have a website served over HTTP that is secure against a web attacker, then if you turn on HTTPS, suddenly this website becomes secure against a network attacker. And of course, this is extremely wrong. And this is one of the reasons for this talk, basically, and the reason why we find so many attacks. So I think you are already familiar with the reason why there is a very, very big power gap from going against web attacker to going against a man in the middle. And some of these reasons are TLS is optional by default in HTTP. It can be removed by the network attacker. You have the very well-known problems of cookies, which are completely helplessly broken in the context of network attackers. Another more subtle one is the fact that TLS has its own identity and session system, and they may not agree with the HTTP ones. And when you have some discrepancy, it's one source of attacks. And the last one is that the HTTPS in the middle is very, very strong attacker. It can run arbitrary JavaScript, because arbitrary requests to honest websites, and exploit some very strong side channels. So you can look at the size of packets, which tells him what is the size of the content that the user is downloading. You can also look at the timing to see what is the patterns of requests, and this is a very good indication of what the user is doing in the browser. Okay, so first of all, I'm going to say what is not covered by this talk, and there are many things not covered. So Hellbleed, it's first of all, Hellbleed from a scale from 0 to 10, it's a 12. So much more powerful than anything I have to say today. And similarly, there have been bugs in GNU TLS, bugs in Safari, and all of these bugs, they have no reason to be. The only reason why we have to face this bug is because we are so angry about performance that we don't care about using some memory safe languages and some well-known verification techniques that could eliminate these bugs. So I'm not really interested in that. Similarly, I'm not interested in the broken PKI problems. We had 2 examples already this year. We had the French government CA issue man-in-the-middle certificates, Indian one as well. The nice thing is that they're getting caught, but bad thing is that it keeps happening. What is in this talk is active network attacks against HTTPS. And you have to realize that many people consider this is a medium security threat, but it's not the case. It's a high security threat because people are connected to public networks all the time. Furthermore, they are using DNS that are not under the control. It's always your ISP, it's your corporation that are in control of the DNS. And through that means they are basically have the power of acting as network attackers against you. And it's the same for governments. We know that on several occasions, the US and UK governments have been tampering with DNS. So really the topic of the talk is TLS exploits that are enabled by HTTP capabilities. And this is what I call beastly attacks. And because they rely on active network attackers, I am assuming that you are targeting websites that are already safe against web attacker, which means that our only targets are the top websites in the world. We are targeting Google, Facebook, Twitter, Amazon, the very good guys. Okay, so when the history of beastly attacks started maybe from the renegotiation attacks in 2009, it was mostly protocol logic flow, but the way it was exploited using a cookie exploit was already an indication that something was wrong. And then we had the wake-up call, the beast attack, which is adaptive chosen plaintext, which means that basically what people believed before beast was that there was no situation where someone would be stupid enough to accept to encrypt thousands of requests that are chosen by the attacker. And what we realized with the beast attack, that it was indeed the case. HTTP does that. And this is exactly the reason why we actually misunderstood these beastly attacks. Then we got more examples that were presented here at Black Hat, crime, breach, many timing attacks, a lot of variants. So I'm going to start with a very good illustration of this kind of attacks, which is called cookie cutter. And it's a poster child for these attacks because it relies on some very, very ancient problems that have been in TLS and in HTTP. And I'm going to show just using standard man-in-the-middle techniques, or you can break security of many, many websites, including Google, Facebook, everyone, just using these simple tricks. So some reminders. As I said, HTTPS is optional. Merlin Spike in 09 showed here that you can do SSL stripping, which is a very effective technique to remove HTTPS from websites. So what we came up with against that is basically strict transport security. It's a HTTP header, which mandates the browser to always connect to this website using HTTPS. But it does have some serious problems. It has a bootstrapping problem, so the client, the browser, needs to see this header at least once. HTTPS is still insecure by default, so there is still no strong way to enforce mandating HTTPS except when you have preloaded HTTPS lists in browsers. But it doesn't scale. And the last problem you have is that SSCS expires. Another reminder about HTTPS and cookies. So this is a very, very serious, long-lasting flaw that has been in HTTP for decades. Is that the fact that the same store is used for HTTP and HTTPS cookies, which means that cookies don't follow the same origin policy. In particular, they are not port-aware, and instead of being bound to one origin, they're bound to non-public DNS suffixes, which is much weaker. So what we came up with to at least protect the confidentiality of cookies is the secure flag in cookies, which is an indication for the browser not to send this cookie over HTTP. However, if you have a cookie that is set over HTTP, then the browser will send it with the HTTPS request, and the server has no way of distinguishing which are the cookies that were set by the attacker and which were the cookies that were set by the honest website. So this is there is nothing new in what I said. This is actually encoded in the cookie specification, where you can read that HTTPS is insufficient to prevent a network attacker from obtaining or altering a victim's cookies. So basically, the attacks are actually explained in the RFC. And if you're wondering what you can do with that, well, it's very well known that you can force cookies. So the attackers is going to use an HTTP subdomain where you can set cookies that will be sent with HTTPS request. And actually, this attack is very old. It's 15-year-old at least. And the impact of this attack has increased tremendously because most of the websites are doing asynchronous actions, which are authenticated without switching pages, which means that there is no feedback for the users that a session has been replaced. And this is also useful for defeating CSRF protection. There was a talk at the Black Hat Europe this year. And the other thing you need to know about cookie forcing is that there is no real defense. So only thing that really works is if you have HSTS with this option that is called include subdomains, and it has to be used on the top level domain of the website, and not you don't have to use any subdomain without first going to the top level domain. Another defense that also exists is channel ID, but it's very weak because it's not supported, and it also has some very significant privacy cost. Channel ID is borderline evil for tracking. Okay, so here I'm going to show you how you can mount a simple attack. You have Alice. She wants to log into Google because she wants to access a document on docs.google.com. So she's going to be redirected to the Google login form. And from there, she's going to send her credentials, so fill in the login forms. And the response from Google is going to have a redirection, so in the location header, and it's also going to set a cookie for the session ID. And because it's Google, of course, they're using secure cookies and HTTP only. However, because of the fragmentation, it's possible for the attacker to stop the contents of this response at some point in these headers. And what the beast attacker can do, he can actually inject himself in the request where Alice is going to be redirected to the Google login form to add some padding to the request. And when Alice is sending the request with the padding, he's going to shift the HTTP header. In this case, you can see the XXX is the padding of the attacker, and now the set cookie header is stopping after the domain, and the secure flag is in another fragment. However, the attacker prevents this fragment from being sent by shutting down the TCP connection. So what happens is that the browser will store this session ID cookie without a secure flag, which means that then on any HTTP request to a Google subdomain, the attacker can recover the session cookie. And this is a practical attack. So here is a demo where I use actually man-in-the-middle software I initially developed for wiretapping search terms on Google. So here, as you can see, because of the auto-complete of Google search, the network attacker can actually see the packets going, and from the size of the response from Google, he can actually guess what are the search terms by the user in real time. And of course, the NSA can also do that. So when you're searching on Google, don't assume that because you're using HTTPS, you're going to be safe from wiretapping. So here, I'm emulating Alice going to either the attacker bait or the attacker injecting itself in some HTTP page. And she's going to go to the logging form on Google where the padding has been injected. And here you can see the man in the middle is slowing things down a little bit. If I was better, it could do that more transparently. So now the victim fills in the login form with the username and password. And the request, as you can see in the attacker window, has been truncated. And unfortunately for me, the location header is after the cookies, which means that the user is not redirected. But as you can see, when I inspect the request, the SSID cookies has been stored without a secure flag. So now you may be wondering, so what I use for this attack is a very old weakness, truncation. It was the reason why we went from SSL2 to SSL3. And there was a presentation about truncation already last year from one of my colleagues at Tenuria. And the HTTP weakness is plain text injection, so the BIS capability, a security depending on the presence of headers or flags, because they can be removed. If you are insecure by default, the attacker can remove your security. And the last thing is the liberal passing of malformed HTTP messages, because when I truncate the message, it becomes syntactically invalid, so it should have been rejected. But it turned out that we have this robustness principle, which say we should accept .g formatted messages. And because of that, my cookie is actually stored on two browsers. So you may be wondering, once this cookie has been stored without the secure flag, I still need an HTTP request to read the value on the network. So I do have to go through HSTS, but HSTS is also something where it's insecure by default. And if you remove HSTS, you lose HSTS protection. So what I do is that I use exactly the same attack to find some redirection on the victim website, to truncate the HSTS header after the max age flag to say that it expires in at most 10 seconds. So the mitigation for that is that you have to reject malformed HTTP messages, and you have to enforce the termination mode of TLS connections. And there are still many. We fix the browsers, we fix Chromium, we fix Safari, but there are still many HTTP clients that are vulnerable to that. For instance, wget, curl, all of those can still be targeted using this kind of attacks. Okay, so now the real the main piece for this talk is a class of attack called virtual loss confusion. So to understand this class of attack, we need some more background on PKI, so you know that you have CAs that issue certificates through intermediates to websites. So as I said before, there are a lot of bugs when you are checking certificates. The go to fail was a spectacular failure this year, but it's not the first one. There have been many others before. And another question that you may be wondering is, can we trust CAs to issue the certificate? So last year, I was an intern at Microsoft Research in Silicon Valley, and we conducted a study with Abadi and Weber, Birol, a few colleagues, about the uniformity of practices in the PKI. And what we found is that the PKI is not uniform at all. So you have some good CAs that are well behaving, and you have other CAs that are complete crap. And the problem we have with the PKI is that the good ones and the bad ones, they have exactly the same power, basically. So I'm not going to say anything more about PKA because it has been a hot topic. It has been mentioned in every year in the past 5 years. So look at the previous talks and academic papers, which are often much better. Another background that you need to understand is the way that we are using HTTPS multiplexing. So an important change we had with the move to the cloud is that it's no longer possible to have one IP equals one certificate equals one domain. It's just too expensive. We run out of IPv4 resources. So instead, what we have is that we have HTTP multiplexing, where you have a server that is configured with multiple certificates. It's accepting connection from multiple IP addresses, and it's managing the TLS sessions in the form of the session database or TLS session ticket encryption key. And what it has to do is redirect requests it receives using the right certificates, managing the session, and sending it to the right virtual host. Okay, so basically when you look at the URI, the red part is the origin, and typically the routing of the request only depends on the origin of the request. What is blue is the path and query parameters, and this is the part that determines what is going to be the response from the virtual host that has been selected. And finally, the hash is kept by the browser. I'm sorry, we need some background on TLS handshake. So it's actually a crime to present the handshake like that, because I have parentheses, I have brackets, and you have to understand that TLS is a complex protocol. You cannot draw TLS as a message chart. You're going to do mistakes if you do that. But in any case, when you're establishing a connection, the client is maybe going to send you an SNI, and it's basically the domain of the origin for the request the client wants to make. However, it's only available in TLS 1.0, but not in SSL 3. Then the server is going, based on the SNI, is going to return the certificate, may also create a record in the session database, which is going to be indexed by the session ID that they may return. Or alternatively, the server can also encrypt these session records under some key and return it in the session tickets later. Let's forget about, we will need to remember what is certificate authentication. The client can also send certificates in the next round of messages for client authentication, and this will be useful in the last attack. Okay, next, resumption. So in the resumption handshake, the point is that you don't want to do a key exchange operation, which is a costly one. So you have two ways of doing resumptions. Either based on the session identifier sent by the client, the server may try to look up for this session identifier in the session database and restore that, resume the key that was used for encrypting this session. Or alternatively, the client may have provided a ticket, which remember is just the same as the session entry you have in the session cache, but encrypted under a ticket key. So in this case, the server decrypts the session record and use that for resumption. All right, now that we've been through this nasty background, what I want to point out is that you have different notions of HTTP and TLS identities, and you need to be aware of that if you are running websites that are using HTTPS. So as a transport layer, you have the server name indication, the SNI, that is sent by the client. You have the certificate that is returned by the server, and inside the certificate, you have multiple notions of domains, so in the common name and in subject authoritative extension. Then you have session identifiers and session tickets, which are also acting as identity, because when you resume a session, there is no re-authentication. So basically, these are working exactly like cookies. You need to understand that these values are exactly working like cookies in HTTP. Whereas, as the application layer, you only have the host header. It's the only truth. And your request should be routed according to that. So when you configure complex HTTPS multiplexers, what you're going to do is configure virtual hosts using some well-known configuration parameters. So first of all, the IP address and port. It's a list and directive. Then the name for the virtual host, which can actually be more than one. It can be a regular expression. But in any case, this is what is going to be matched against the SNI and against the HTTP host header. Then you configure what certificate is going to be used for this virtual host. And you also need to configure a lot of complicated things about your session cache and your session ticket. Of course, people get that very often wrong. So you typically have to use some tools to check your configuration. But what really matters is that for the request routing, the HTTPS multiplexer, first of all, always matches the IP endport of the incoming request to the IP endport of the chosen host. This is a basic rule, which is not a good rule, actually, because IP endport are not, they're under the attacker controls, they're not under your control. Then the settings for encrypting, for creating the TLS session are going to be picked from the host whose name matches the SNI, if one was given, because SSH doesn't have one. So there is what is called a fallback mechanism. You have if the server cannot find a matching one, it's going to use a default, which can either be explicitly default, or it can be the first one in the configuration file, basically. And it's exactly the same for routing the request to the virtual host. So you're going to match the host header that you receive against the names of the virtual host. And if you don't have any match, you're going to fall back to the default or to the first. So what is extremely important that you have to remember from this talk is the fallback mechanism. So you don't have any guarantee that the selected virtual host that, for routing the request was the one that was actually intended to handle the request. And I would like to point out that this is not a new thing. It's actually a known vector. And there is a very good paper from CCS 07 by the Stanford crew, where they are doing what they call DNS rebinding. But in their model, actually, it is the client is connecting to a malicious website, and the malicious website is rebinding its own IP addresses to many other domains on the internet, and using the host fallback mechanism to use the client as an open proxy, basically. So this is an attack against the client. But what these people missed is that if they had done the same attack on the server, the results and impact is much worse. So let's take a simple example. You have two TLS servers, same domain, different port, sometimes used. Well, you may maybe know that actually the port header is the port is included in the HTTP host header, but it's never enforced, never. So the attacker can redirect freely between ports. So the port is useless for some origin policy. Another simple example, you have a certificate that covers two domains. You have one server at one IP X that handles the first, another server at IP Y that handles the second, and they both use the same certificate. So what happens when the attacker redirects the packets from a request from X to Y? The answer is that Y is going to return a page from y.a.com, but this page is going to be served inside the x.a.com origin. So the point about host confusion attacks is that they rely on several things, but mostly the virtual host fallback. So the way that you want to exploit that is you want to transfer weaknesses and vulnerabilities, such as cross-script scripting, user contents, open redirectors, cross-protocol redirections, X-frame option, course, anything, basically. You want to be able to take that from one origin and move it to another one. And it turned out that someone had already done that at Black Hat. It was in Black Hat 2010 by Hansen and Sokol, and they had a demo where they transferred XSS between two Mozilla domains. And I think, unfortunately, they did not realize the significance of their discovery, because this is actually a very generic attack vector that can be exploited in many ways. Okay, so first one I'm going to demonstrate is very simple, cross-protocol redirection. So say that you have, I'm actually targeting OAuth tokens here, which is a very fragile security thing on the internet. It can be broken extremely easily. So as you may know, the redirect URI of OAuth is actually origin-based. It's not domain. It's not a full URI. It's just origin. So this is the place where if you want to use login with Facebook, for instance, this is where Facebook will redirect the access token to. It will be stored in the URL fragment, the hash, and as I told before, it's a part that is kept by the browser. So here I'm going to show that cross-protocol redirection can actually be used to take OAuth token that was on the HTTPS domain, do a virtual confusion to some other domain in the certificate, and in this origin, you actually have a redirection to HTTP. And by doing this redirection, the attacker is able to recover the access token. And it's very interesting that it's actually an attack that is built into Google. I learned that if you rebind google.com to noSSLsearch.google.com, suddenly your search queries are going to be redirected to HTTP, which means that you have to assume that Google doesn't care about the confidentiality of search requests, because it allows network attackers to remove the confidentiality of search requests. So here's how the attack plays out. I'm using Facebook login here. So Alice is going to use login with Facebook, where she's going to be redirected on Pinterest in this case. So Pinterest has let's say Pinterest has two servers. It has one www.pinterest.com, which is a very secure origin, HSTS, everything, secure cookies, whatever you want. And then you have another one, which is api.pinterest.com, which is a wildcard certificate. So what we're going to do is take this request that contains the Facebook redirection from that contains the access token, and we're going to move it from www.pinterest.com to this API server. And it turned out that this API server, when it receives a request it doesn't understand, it will redirect it to HTTP for some reason. And you will be surprised at how many websites do that. Many, many domains have a page that redirects to HTTP. And when you do that, of course, the attacker can recover the token from the HTTP request. I'm going to skip this demo because I have more interesting ones. But the next one may be more exciting, maybe. So it's OAuth confusion with your user content origins. So it's very common to use different top-level domains for user contents. For instance, Google uses googleUserContent.com, Dropbox uses dropboxusercontent.com, and it's very good practice, except if you're mixing google.com and googleUserContent.com in the same certificate because of virtual OAuth confusion. But here, what I'm going to target is when you have the user's own files. Because it needs to be authenticated, there needs to be access to a session cookie. So it has to be on a domain where the session cookie is available. And this is very interesting for us, because we can try to target these domains. In the case of Dropbox, these files are on dlweb.dropbox.com. This is when you're looking at your own files on your Dropbox account. And I'm going to use one of my favorite exploitation tricks from HTTPS attacks, which is short-lived cookie forcing. So you're going to force a cookie that is going to temporarily replace the session of the user with the one of the attacker. But I set a very short expiration time for the cookies that I am forcing, such that after a few seconds, the user session is restored. And this allows me to break into the high-trust Dropbox.com origin, which is very, very, very well protected, and recover the victim session. Well, let's see how it plays out. So here, we have the attacker's Dropbox, and the attacker has stored a malicious file which contains the attack. So it's a HTML file that has some exploit. So I think I opened this file, and here you can see that this is a way to take control of this origin. But right now it's served on DL Web, so I cannot do much with this. So to be useful, I need to be able to show this page on the user. And for that, I'm going to do virtual OAuth confusion on the victim between the www.dropbox.com and the dlweb.dropbox.com origins. So for that, I need to take, let's see. Yes, so I'm moving to DLWeb. And here I am grabbing the attacker's session cookie. which I'm going to force on the victim using a very simple script. So once this is done, the next step is that you have to bait the user into some page that will do the cookie forcing. Or you can, of course, always inject yourself into any HTTP request made by the user. So this is the victim's browser. I use a different one, it's Firefox. So here, there is some picture that actually is causing the cookie to be forced. And as you can see here, I have actually redirected the user to the DL web, but under the www.dropbox.com origin, which means that now the cookies that I have forced expire, and I get access. I have control of an XSS page in www.dropbox.com that is using authenticated under the victim's account. Okay. Another very, very interesting way of exploiting virtual confusion is shared session caches. So as I told you before, you have three kinds of authentication in TLS. You have certificate, you have session resumption by identifier, and you have session resumption by ticket. And it turned out that when you're doing cloud hosting, you really want to use multiple servers that can have resumption work between them, because they may be redundant servers for the same content. And a good way of doing that is either having a network session cache or having a shared ticket key. So it's actually quite dangerous when you do that. And we found that the session cache was not well partitioned between many cloud providers, including Amazon, Mozilla, and Yahoo. And interestingly, the cache isolation was defective not on the ticket, but actually on the classical session database, which means that you had servers that were serving different websites, even different certificates, which is very interesting. But if you wanted to exploit that, you need to make sure that session identifier-based resumption is used. And since they were also actually using tickets, and tickets as precedence over session ID resumption, you need to downgrade the connection to SSL3. And it's one of the things that, amazingly, the network attacker can do because of browser behavior. They allow you to downgrade connection to SSL3. I'm also going to skip this demo, and I encourage you to look it up online. So the most interesting case I'm going to show is when you have shared reverse proxies. So this is when you're talking about the CDN settings, for instance. And they're actually very commonly used. Many SSL terminators, CDNs, things that are actually routing requests back to some backends, but not serving anything locally. And their handling of TLS is often acquired. So on Cloudflare, they do domain packing, which you consider quite bad. And you'll see why next. Another good, interesting example is Akamai, where they actually allocate dedicated IP addresses for the customer certificates, which is impressive. And other cloud providers are using SNI-based routing for their reverse proxies. And interestingly, what is the fallback virtual for these reverse proxies? And we found some very interesting cases, for instance, on Akamai. So I did remember that I saw this page, which was written in year 2000 about Akamai, that explains how you can use Akamai as an open proxy. So basically, you dial some number, use 666, of course, and then you put the domain you want the request to be sent to, and the Akamai server will actually download this request, send this request, and return back the result to you. And here, of course, I'm going to use that against NSA website. So this is the real NSA website, the real NSA certificate. And what I noticed is that it's valid for www and www2, and also just NSA.gov. And also, I also noticed that it is served by Akamai. So next, what I'm going to try is I'm going to see what happens when I send a request for one of the domains that is not used by this Akamai reverse proxy. So for instance, in this case, it is nsa.gov with no www. So this is the request I'm sending. And in the response I see from the Akamai server is actually a page on Yahoo. And this page from Yahoo is served through a request with a host header equals to nsa.gov. But the point is, if I send this request over HTTPS, it turned out that since the Akamai server is configured to use an NSA certificate that is valid for nsa.gov and the other two, well, I'll let you imagine what happens when I do that. So I just dial in 666, I put my attacker address, and here you go. I am the attacker, and I have impersonated the nsa.gov origin, which is about as bad as you can get for HTTPS attacks. And this is a real NSA certificate. So remember, the demos are on bh.ht.vc. And it turned out that this is actually terribly bad because every big website uses Akamai. So what kind of website you can compromise with that? Well, here is some examples. So I'm going to show that you can impersonate. So in some cases, you can just impersonate some minor subdomains that are not used. So on Twitter, you can just, for instance, since you impersonate this subdomain, you only have access, for instance, to the cookies for Twitter, which is already quite good. But in other cases, like LinkedIn, the certificate is a wildcard one, so you can actually impersonate .linkedin.com, which means that you can serve any page you want through this origin, and you can get the user to fill in a password. So this is quite bad. And the other thing that's interesting is that this doesn't leave any trace, because when you have a virtual host fallback, there is no trace in the log, actually. The request is logged under the default name. So what can you do to prevent host confusion? The first rule of thumb that you have to enforce is that you should not mix low trust and high trust domain in certificates. It's not a good practice. If you have any virtual host confusion between them, the low trust one can probably compromise the high trust one. I showed some examples, but I actually do have more. The other thing that you should always do is configure a fallback host on every IP on your servers. And this should return an error code. And this is already a known security advice, but you should really take it to heart. Other thing is your TLS session configuration. It's actually very security critical that you do not set some shared cache between virtual hosts that have different certificates. It can be disastrous. And you also need to be worried about configuring some encryption keys for tickets, because they may cover more virtual hosts than you expect. So the last part is a very interesting one. I'm going to tell you how I came to that. I was discussing with Nginx developers about how to better isolate the TLS session cache in Nginx. And one of the things I was suggesting is that we should ensure that the SNI of the connection matches the host, HTTP host header of the request to prevent the resumption case where you have non-matching SNI. And what they told me is that they could not do that because in some cases they were required to accept this kind of mismatch when they were using SPDY. And of course I was extremely surprised. And it turned out that actually there is a feature which is called SPDY connection pooling. And what this feature does here is that normally when you have a server with two domains and you have requests to these two domains, the browser is required to create new HTTPS connection for each. With SPDY, the idea is that why don't we reuse the connection we have, because we already saw the certificate and we remember that it was valid for these two domains. And the only thing that is required to enable that is that the DNS of the two domains have to point to the same server. And of course, this is a condition that is under the control of the attacker. So I was extremely surprised about that, because it turned out that everything I thought I knew about HTTPS authentication was wrong. And I started writing down some stuff. And of course, last week, I realized that all of our results did not hold, and that if you had some session-specific guarantees, they will be actually leaking to every domain that you have in the certificate where this property was established. And remember that this is also present in HTTP2 drafts. So of course, last week I discovered new attacks. And I cannot talk about them. I would have loved to show another impersonation of NSA.gov. I could do that, but it's not patched, so I cannot. Okay, then I'm going to talk just a very, very little bit about triple uncheck. You may have already heard about that. I think I don't really want to go back to the original renegotiation attack. But what I do want to say is that we had a mitigation, and we were thinking of this scenario. So the upper one is a 2009 renegotiation attack, where the client wants to connect to some server, and you think it's creating a new connection, but in fact, the attacker is tunneling this handshake inside another one you already created with the server, which means that the attacker is able to inject some data that is going to appear before the user data. In triple handshake, we're using some very interesting thing about TLS is that you are able to synchronize the keys between sessions. And the way this works is you have two ways this can work. So in RSA, you just encrypt the pre-master key that is created by the client and sent to M. So in this scenario, the client is connecting to the attacker willingly. And the thing is that you can have another session that is created with some other participant, some other server somewhere, that is going to use the same cryptographic parameters. And once you do resumption, you can move a connection that was established with M to a connection that is established with anyone else somewhere. And every security guarantee that was bound to your session, they may be leaked into whatever is going to be transmitted to the session with this unknown participant. And the problem you also have is that the belief on both sides are different. So the client's perception of who is talking to does not match the server perception of who is talking to. And I think the very interesting point that we make about this attack is that we do have an exploit. It's an exploit against client authentication. And it turned out that nobody really expected that such an attack would be possible because when there was the original renegotiation attack, there was a lot of security analysis on the session system in TLS. And the reason we miss that is very simple. It's basically because, because the preconditions of the original renegotiation attacks, they have been left untouched between the time where they were found and the time the triple uncheck was discovered. So, for instance, the fact that you have concatenation of data between TLS connections that were from different handshakes, or the fact that the server certificates could change during renegotiation handshake. And these were weaknesses that were left unattended after the renegotiation attack, and we actually managed to find some new flow in TLS to re-exploit them. It's really quite surprising. So I think the very important point is that we really want to have robust solutions to these failures. And when it's the same pattern through all the talk, I always did the same thing, which is to reuse very well-known vulnerabilities that had already been exploited before, but the patches for them were not robust. And because of that, I could always find new ways of exploiting them. And so for the traffic mitigation, we actually proposed a very drastic change to TLS, which is to change the key derivation. Cryptographically, it's a major change. And we're very surprised because this change is actually accepted. So maybe someday we'll actually be able to change cookie behavior. You can always dream. All right, so the conclusion for my talk is that there are many lessons to learn from HTTPS-based attacks. So for instance, cookie cutter, parsing is security critical. This is very important. We found many attacks in HTTP because of URI parsing in JavaScript. Don't do that yourself. And remember that not every string is a valid input. So there are some input that you need to reject. Okay, so another thing is that you should not rely on the presence of something to be secure, because additions can typically relax things, but not make them secure. Otherwise, they can be removed by the attacker. And also, there's interesting about side effects and data that is processed before the integrity of the data is confirmed. Really, the main lesson I want you to learn is about virtualized confusion. What we want when we are doing cloud services HTTPS multiplexers, SSL terminators. What we want is to routing only to depend on authenticated input, which means that no matter what kind of tampering the attacker is doing to your request routing, is going to have the same outcome. But it is also must be the case that the routing is consistent across servers that are sharing credentials. And what I mean by that is that if you have two servers that are using same certificates, then the routing behavior of requests needs to be the same on these two servers. Otherwise, you're going to have virtual exploits. And what I want you to remember is that it is currently, in current HTTP server, it is your job to achieve authenticated, consistent routing. It is not going to be provided to you automatically by the server. It's in the way you configure your server. So it's your responsibility. And the second thing I want you to be very careful about is the same certificate policy. I told you that in SPDY, connections are going to be reused for requests on other domains as long as they appear in the original certificate. So this means that you need to be extremely careful about what domains you put together in the certificate. And you should also be aware that, for instance, if you're using Cloudflare, your domain may be included in a certificate that contains malicious domains. And of course, this is very bad for you. And it's probably, I expect there will be more attacks. From Triple Handshake, the main lessons we learn is the API problem. So TLS is really, the problem we have with the TLS API is that every difficult decision is handed off to the application. So basically, they get that, of course, very wrong. And the other thing is that the crypto values from the handshake are not identifier for session participants, but this is not a lesson for you, it's a lesson for the IETF. Okay, so to conclude, what we're doing about all of these problems, we have a verified implementation of TLS to prevent go-to-fail bugs and heartbleed type of stuff. And what we want to do is to actually consider HTTP and TLS as a single unit of verification, because if you are taking the security guarantees of the TLS API and the security guarantees of HTTP separately, then you're never going to be secure. They have to be considered together. All right, so we don't have a lot of time for questions, I'm afraid, but feel free to come to me at the end of the talk. We only have 2 minutes for questions, but I will be happy to take at least one. You do have a microphone here. Okay, we don't have questions, but feel free to come see me after the talk. I would be happy to discuss these issues with you.